Video. Our next talk is an overview, wrapping up a little bit of the architectural elements we have learned to get to know over this week, and Josep kindly volunteered to give an overview of a very specific architecture, which is our working BeFEMTO architecture. So it's an architecture which tries to incorporate femtocells into the overall cellular game. Now, Josep is with us for a long time. You joined actually much earlier than I did. So 2003, I believe.
Yeah.
So he has done his PhD at UPC, and he has a very strong networking background, and he's leading the IP group here at CTTC. Voila, your floor is all yours.
Thanks, Misha. So good morning, everybody. So as Misha said, what we are doing in this presentation is to give a brief overview of the BeFEMTO system architecture, and not, well, system meaning that it covers all layers. And since this presentation, we will use it also as an intro for the rest of the presentations that you will have this morning. We will, in the last slides of this one, we will focus more on the networking issues that we're dealing with in some specific scenarios that we consider in the following presentations. So Jaime, who will present afterwards, and Jose, who will present also afterwards the routing part. They both work here in the IP technologies area of the CTTC. And the last author, let's say, is Frank Starkey, who is the technical manager of BeFEMTO, and to whom we owe, let's say, most of the architectural reasoning of BeFEMTO. And besides, I borrowed some of his slides, so that's why he's co-author too. So to start with, the first important thing that you must bear in mind is that BeFEMTO is an IP. It's an integrated project, so it's a large-scale project, let's say, with big budget, and with more short-term orientation than smaller projects like STREPs. So this means that we have more constraints from the environment, from industry, for example, in this case. And in this case, since we are dealing with mobile networks, most of our constraints come from 3GPP specs, of course. So what you're seeing in this figure, you already saw it in Thierry's presentation during the first day, but what you're seeing in this figure is basically what BeFEMTO does, both at the, let's say, what the 3GPP calls the radio network layer, which is from this line and above, and also what does BeFEMTO do and how BeFEMTO handles the transport network layer, so what is below carrying the packets. So what you see is that, of course, we are constrained by the EPS 3GPP architecture, but BeFEMTO expands it. Right? We are doing improvements in RRM, in SON, also in the networking issues related with procedures, and these networking issues are also affecting the transport network architecture. So in this case, it's not 3GPP who defines it, because 3GPP specs define the radio network layer, right? But particularly if you introduce elements like femtocells in a network where there is part of the network that is not fully under the control of the mobile network operator, like the ISP providing the broadband connection to the femtocell, the operators want to make sure that the user that is using its spectrum is receiving the quality of service it's supposed to receive. And that's why 3GPP started to discuss on how to make both worlds interoperate somehow. And they started to discuss with organizations coming more from the fixed world, like T-SPAN or the Broadband Forum, so as to define interfaces to provide these resources, the appropriate resources to guarantee this quality of service for the user, right? So improvements in the radio network layer compared to what 3GPP defines, because we're considering more scenarios and new algorithms, and improvements in the transport network layer also. And what you see here is two key, let's say, building blocks of the BeFEMTO architecture, because that's where we put most of our innovations, let's say. We also modify some other entities, as you will see in the next slide, but the Homing Node B, of course, the project is about Femtocells, so the Homing Node B, we're modifying it. We're putting a lot of new mechanisms and schemes. And we're also introducing a new building block, which is key for a specific scenario out of those we are considering BeFEMTO, which is called the Networks of Femtocells scenario. And this building block is called the Local Femtocell Gateway, whose goal, as you will see, is basically to somehow isolate traffic in, let's say, a local network where you deploy some femtocells so as to offload both in terms of signaling and data plane the core network of the operator, right? So these are two of the main key building blocks where we do things in BeFEMTO, the local femto gateway and the Homing Node B. So don't worry about this architecture. It should sound more or less familiar from the first day, Andrea's Mather presentation from NSC. The most important thing about this slide is the code of colors, let's say. Right? In BeFEMTO, we are doing new things because we are not only considering, for example, we are considering 4 types of scenarios. We consider a regular one, a standalone femtocells. We consider also relays, outdoor relays. We consider mobile relays. And we also consider networks of femtocells, these 4 scenarios. So for the standalone one, you could have a Homing Node B. No problem, we are improving the Homing Node B. Then what you see here is the modifications that we do to the different sorts of relays that we are introducing and the schemes that we're introducing. So whenever you see orange color over there, is that BeFEMTO does either it defines a new entity in the 3GPP functional architecture, or it modified it, right? So this is what orange means, basically. And as you see, most of our work and innovation is focused over here. So mainly the EU-TRAN, and for the networks of femtocells also in the local femto gateway here, right? And for the core, which are the white entities over there, the P gateway, serving gateway, most of it is white. So meaning that we don't touch much. Of course, we do some things. For example, we also, and the notation is the same for the interfaces, right? For example, in this case, we defined, NEC did, a new interface in case you wanted to keep your local connection when you were in a network of femtocells and you move outside to the macro. If you want to still have access to your local services, sort of a VPN if you want, with session continuity, you're using this interface that they define, right? So in that sense, we also modify somehow the P gateway. But if you don't need this session continuity, you can probably skip this orange, this light orange part. And another entity that we are modifying in the core is the management part, because we're introducing a new node and we want this node to be upgradable, to upgrade the software and to like send it policies and see how the whole thing is going. The other important thing about this picture is that this is the operator domain. So all these functional entities are managed by the operator. And the main difference with this one is that this entity, which has, as you will see, certain additional functionalities that traditionally assigned to the core, let's say, part of them are moved to the customer domain, right? So the management of these entities here will be shared between the mobile network operator and the local network operator, right? So this is the other important thing. So in summary, we mostly don't touch the core, let's say, and we focus our innovations over here, right? For considering all these 4 scenarios that we define we are studying in BeFEMTO, right? So that was for the radio network layer, the 3GPP part, right? Let's move now to the transport network layer. And the transport network layer, and what you see here is the reference architecture from TSPAN, right? So this is one of the organizations standardizing what transport network should do. And as we said, the 3GPP, the 3GPP world in this case is represented by the upper part of the figure, has defined some interfaces to interact with this transport network. Okay? But as you see, most of it is white. We are not touching anything here. So the figure is just to mention that, for example, in terms of authentication, there's an entity defined by TSPAN related to that has an interface with the entity associated with authentication and subscriber information in the 3GPP world, right? And that's the interface that they define for that, for example. And the other important thing is that the entity which is responsible in the 3GPP world to handle quality of service and policy control and the resources assigned to the users and each bearer from a user, these kind of things, is associated to the equivalent entity defined at the transport network layer. So that's why they define this interface also. That's the main message of this part of the slide, right? So of course you have a mission control part for the transport. You have a network attachment subsystem which handle authentication, IP address configuration to the different nodes in the access, and this is the part handling the data plane and enforcing the resources that you negotiated through these interfaces, right? But as you see, most innovations are here, and in particular, if you recall, these entities are the ones we defined for the network of Femtocells scenario, which is the one we are most interested in these talks today, the ones that are coming from now on. So what we have is that we define new interfaces between some of the entities that were previously defined and the new entities that we introduce. RT, for example, is for routing, for exchanging our specific routing information. We will give more details afterwards. LM is for location management, because we design a distributed location management, and you will see it afterwards. Well, we define all sorts of new functionality also at the transport layer, mainly focusing on the network of femtocell part, right? But in the customer domain, okay? Most innovations. So, at the logical level, and this is let's say, one of the key goals of introducing the local femto gateway, what are we doing there? So what we are doing by introducing the local femto gateway is to try to constrain. Imagine that you have a local femto gateway in a company, in a stadium, whatever, you may be interested in deploying a lot of femtocells, but you don't want all these femtocells for each of the signaling messages for handoff or whatever. You don't want them to reach always the core. So you want to constrain both the control and the data plane traffic, if possible, to the networks of femtocells. So you introduce this new entity, the local femto gateway. And the way you somehow isolate the core from the operation of the networks of femtocells is by moving part of the functionality of the core to this new entity, which is this P corresponds to proxy. It's proxy MME, and you put a proxy serving gateway here. This is for the data plane, and this is for the control plane. So somehow, from the point of view of the core network, all the UEs that are attached to these hominode Bs look to the core network as if they were attached to a local femto gateway, which acts as the hominode B. Right? So we still maintain the S1 interface. So we are using standard messaging here. So from the point of view of the core, this is as if it was a hominode B. Yeah, single one handling all the UEs handled by each of these hominode Bs. And from the hominode B point of view, this looks as a core. So still you have the same S1 messaging. But in fact, you have introduced this one with the advantage that you constrain some control, for example, inter-hominode B handoff in here could be handled by this node, and the mobile network operator does not notice anything necessarily. So you just send to the core the really relevant messaging, or when you hand out to the macro, and then you need to, of course, send messaging to the core. But otherwise, you constrain it. And this is the advantage of introducing the local femto gateway. And as I said, what you are seeing here is the BeFEMTO hominode B architecture. It's not just for networks of femtocells. In this case, it's the whole picture integrating all RRM, so on, and everything. Let's say that the network of femtocells one has some specificities that probably, with higher probability, you will find more innovations. And for other simpler scenarios, probably you will have less innovations, let's say. But what do we have in this figure? So protocol stacks, this one handling the communications towards the UE. So regular one, except that we also modify in Word Package 3 of BeFEMTO the lower layers, the physical layer, RF stuff and baseband stuff. You had a lot of that in the past days. And this is the stack handling the interaction with either the local femto gateway or the core if you just have a hominode B, right? And you have stacks for all sorts of things. For example, for management, this one is more related with security and authentication. This one is more for the control plane, and this one is for the data plane. So this is for the central part. And then you have in the right part everything related with SON and RRIM. So probably Misha already explained you something about that yesterday, but the basic idea here is that this is the main building block. This is kind of the brain, so where that tries to gather information in terms of management from the operator, so the policies to apply. It also gathers information from the SON enablers like position, coverage estimation, any other thing that you might want to acquire for taking the decisions for optimizing the operation of the network. It also takes information from the network monitoring building block. And with all that, and knowing the policies of the operator, and knowing which of these specific building blocks, with each of them implementing some specific function, like coverage optimization, mobility load balancing, and all this stuff, knowing which of these are implemented in the femtocell, and knowing the policies, this building block configures this one, all the mechanisms in this one, which are all of these, with the specific configuration parameters to achieve a certain goal. And of course, this has an effect on the scheduler, how you schedule resources and all that. So for the left-hand side, we have the management functions over there. For example, operators are, as I said, operators are worried of having a part of the network that they don't control in the middle when you deploy a femtocell, like the broadband ISP connection. So folks from Telefonica were working on distributed fault diagnosis. So they put probes all over the network, and they try to infer where the problem is, if it is their fault or is the fault of the ISP, for example. They also deal with nice ways of authenticating devices when you deploy them. Also, network management, as I said. But for the rest of the talks, we will focus mainly on these parts over there, which have to do with this new innovation, which we call the geo sublayer. Geo in the sense that we are exploiting geographic information for taking forwarding decisions, because it has some nice features for us, as you will see afterwards. So you will see Jaime will give a talk on local location management, which means basically identifying UEs inside the network of femtocells in an efficient manner. And Jose will talk, and myself also, a bit on routing, a distributed routing solution for wireless networks of femtocells. This was for the hominode B. What about the local femto gateway? So what you have in the upper part is the management part, and what you have in the upper in the lower part is more the control and user plane part. So for management, you might want to have not just decisions taken at the homing node Bs. Since you have, let's say, a special kind of node, which is the local femto gateway, where you can somehow centralize functionality, you might be interested in centralizing functionality there. For example, the fault diagnosis one. So you get information from different probes in different homing node Bs, and in the end you take the decision. So the inference decisions where the problem is, for example, you might take one of them in the local femto gateway. You might also measure interference with network monitoring modules in each of the homing node Bs, and decide to switch off a certain femto, for example, from this centralized point based on the reports that you receive from homing node Bs. Well, this is about, let's say, policies that could be interesting to centralize in the local femto gateway for the more efficient operation of the network of femtocells. And this part over there has to do with, well, you already know the proxy MME, the proxy serving gateway. For LIPA and SIPTO, we also have sort of a P gateway here to be able to directly send traffic to the internet, so that it's offloading, basically. Or this interface that I mentioned before for handing over between the macro and the networks of femtocells when you are accessing local services, for example. And you also have the routing, which, for example, NEC was interested in a routing that was centralized, a la OpenFlow. So if you know OpenFlow, you have a central controller, you receive information for different nodes at the transport network layer, and you centralize the decision of the routes to take. And then you send commands to each of the switches in the network so as to enforce the quality of service that you decide, or whatever parameter that you want to enforce, right? So they did it centralized. What you will see afterwards, we will present with Jose, is a distributed solution. So we don't have this. We have this routing distributed throughout the homing node Bs. And well, that's more or less it about the local femto gateway. So what we were discussing up to now were, let's say, functional architecture, and this is only to show that this is an instantiation of a network of femtocells. Well, you might have, in fact, more local femto gateways than one, depending on the scale of the network. And this is, well, these are homing node Bs, and in particular, in the following talks, we're especially interested in all wireless networks of femtocells, like the one that the Femto Forum representative presented during the first day, where you, for example, you have Wi-Fi in a femtocell for the backhaul in a rural environment, and you have well, 3G or LTE access to provide communication to regular users, right? So we're interested in this kind of scenarios, and in particular large-scale scenarios like these ones. And just to tell you where we constrain our research in the following talks. We constrain our research and all our schemes just below the IP layer, which means that we are working at the transport network layer. It has some minor implications at the, let's say, the radio network layer, at the 3GPP world, but we constrain our innovations here. So what is this? This is the protocol stack, for example, for the UE, user plane. This is user plane protocol stack in all the nodes involved in our communication towards the core. This is the UE, and that part is the core, and then you would have the P gateway. So, so the UE has a regular stack. This is also a regular stack for what we call a wireless homing node B, because we have a wireless backhaul. So it's a femtocell with a wireless backhaul. Then we put a Wi-Fi interface, and the intermediate homing node Bs, wireless homing node Bs, act as wireless mesh routers, if you want to call it like that, right? So you just use this part of the stack when you are forwarding, helping other homing node Bs to make packets reach the local femto gateway. And in the local femto gateway, you still have this part, but towards the core, you don't modify anything. So all our let's say, innovation is constrained to the networks of femtocells, to the nodes in the network of femtocells. Same thing for the control plane protocol stack. For us, messaging for S1 IP procedures, everything are packets. So we take these IP packets, we put them in a geo packet, and we take decisions on routing, for example, based on this geographic information, but always inside the local femto, the network of femtocells. Sorry. So in the end, our goal is to support all sorts of flows in the BeFEMTO networking architecture, in particular in the all wireless network of femtocells. This should read local femto gateway. It's an old figure when we were deciding the name. So you could have SIPTO traffic directly going from the local femto gateway to the internet. You could have traffic going to the core and coming back. You could have LIPA traffic, so where the local femto gateway is in charge of constraining the traffic to the local network. Or you could even have traffic, and our distributed routing allows that. The problem is that the 3GPP specs would not allow you to establish this kind of beers on a permanent manner. You can use this communication in the data plane when you're doing handoff, but in an interim manner. So if you want quality of service and all that, we're still working on that. Though our routing protocol at the transport layer allows us to do it. So in the following talks, what you will see is Jaime will present you local location management. Jose and myself, we will talk about routing, both from a more, let's say, theoretical and simulation point of view. And then we will move to a more practical part where mainly Jose will explain you how he implemented the distributed back pressure routing that we are presenting afterwards over the testbed with some measurements, and if everything works, with a demo. Live demo, let's say. So if you're interested in what we defined at the system level, at the architectural level in BeFEMTO, your reference is this one. This is the main one. If you're interested in more specific details on the schemes more related with networking, these are the two reference ones, and they are all publicly available. You just need to give your name and that. You can download them. And that's it.
That was very good on time. Thank you. Any questions on the architecture? I think there will be more discussion items maybe later on when we discuss the actual embodiments of the building blocks. So thank you very much, Josep. Thank you.
Okay.
Coffee break now, but